Next problem is called longest palindromic substring, and we are given a string S, and we have to return the longest palindromic substring in S. So we already know what palindromic means. Basically, it means that it reads from start to end the same as it reads from end to start, and the substring is basically any continuous sequence of letters inside of the original string. So, for example, BAB inside of the string BABAD is a valid substring, and it's also palindromic because it reads BAB from start to end and also BAB from end to start. So basically, that palindromic substring is the longest one. Also valid one was ABA. So we can have multiple ones of the same length that are palindromic and that are valid substrings, but we can just return any of them. And in the second example, we have BB as the substring that's palindromic. We cannot combine it with any other letter because it will break the palindromic property here. So the constraints are the following. The length of the string is from 1 to 1000, and the string consists only of digits and English letters. Now for the for this problem, and when we read it, it's actually one sentence, and to find the best tool in our arsenal of algorithms is to actually break it by phrases. Now we know how to do the palindromic. We know what palindromic means. We know what the substring means, and we know what the longest means. So how do we actually arrive at an algorithm? Whenever we have this longest substring or any other property of a specific configuration of the original string, in this sense, configuration basically means just choosing a subset of letters inside of the original strings that maximize some property while keeping other property. So we want to maximize or minimize, but in this case, we want to maximize the length of that configuration while keeping the property of having a palindromic configuration. In this case, just a subset of strings. And also because it's a substring, not a subsequence, we know that the third rule has to be that we have continuous sequence of letters. We cannot use, for example, if we have B, A, B, and then we have, I don't know, A, C, we cannot just eliminate A and say, okay, B, A, B, and C is a valid substring. It's not valid substring, it's a valid subsequence, but we are here looking for a substring. So continuous sequence of letters inside of the original string. And because we are having these properties, it usually really leads to a DP problem, calculating the longest subsequence, longest substring, longest anything, basically by maximizing, because we are looking for the longest, so it's a maximization process, maximization problem, dynamic problem. And when it comes to strings, we can have two strings usually that you are kind of comparing or trying to find, like matching something, like matching substrings or anything else. Maybe we can calculate Levenshtein distance to see how many, what's the difference between the two strings. In that case, the dynamic programming approach is to basically form a matrix. If the string length of the first string is m and the string length of the second one is n, then we'll have n times n matrix. So we'll have, for example, hello, and we'll have here world, for example. So we will have this matrix here, and then we will basically calculate each of these values, numeric values here, in some fashion given by the problem statement. Here, actually, we only have one string. And when you have a one string, it's always a quadratic matrix. When we want to see some property and we want to apply the dynamic programming principles, it's always n times n matrix. So we are basically, instead of having a second string, in this case world, for example, we can just copy hello. So we will have n times n for the matrix. But how do we actually solve? How do we calculate the maximum substring, maximum length palindromic substring? So here we have basically a substring, a string, original string, A, B, A, B, A. And in this here, and the length is of course 5 here, so we have n times n matrix. Now, the question is, how do we define this matrix, which we'll call dp? How do we define, for example, dp I, ij? How do we define that? So if we say that the rows are representing the first, basically the starting point of the substring that we are calculating the dp for, and if the j's, basically the columns, are representing the end of characters, the end character of the substring that we are currently calculating the dp value for, then the dpij would basically compute the dp value for a substring of the original string starting at I and ending at j. So in the first row, we'll basically have a substring starting at A, and then for each column, we'll basically have a substring A, just A, because it starts and ends at A. Then we will have AB, then we would have AB A, then we would have AB AB, and then finally we'll have basically the same, and then we'll just add add the A. So what we are basically moving our J pointer to the right. So we are increasing the length of the substring. We are increasing the substring that we are calculating the dp for by moving the right pointer to the right. Then if we move to the second row, then we are basically omitting the first character. The longest substring that we will be calculating the value for will be BA. That's basically starting from the second letter of the original substring and then moving to J up to the last letter in the substring. So the dp ij will basically represent a flag that can be either true or false, depending of if that string is palindromic or not. So the first thing that we know is that a single character, substring with a single character, with only one character, is always a valid palindromic substring. So we know that on the diagonal, so starting from A, ending at A, so we have only this letter. Starting from B, ending at B, we only have this substring, and so on. We will have all truth. And we also know that we don't have to calculate this side of the matrix. So we have a kind of triangle matrix here. So we don't have to calculate this because it's not a valid substring. Because let's say I have BA, basically that means that I'm starting at B and then to get this A here, which I cannot do. I cannot go backwards in this substring. So we only have to calculate these. And while we're calculating, we are also gonna hold the reference to the maximum length of the substring, and we can easily get that by just doing j minus I, because I is the starting position, j is the ending position, plus 1, because they are both inclusive. And that will be basically the length for each of the dp's that we have calculated the value for. If it's true, then we can calculate the length of that substring, and we can check. We know that's palindromic because this is true, and we know that we have some max length, so we'll try to update it. And finally, then we can just return the max length. We will also keep the references to the start and the end of the maximum length palindromic substring that matches the j minus I plus 1 length that we once we update the max length. So the only question here actually is, how do we update the rest of the triangle? So the rest of this triangle here. So we had to use previous values in order for us to calculate the rest of it. So it's not kind of clear immediately, but the natural way of doing it would be to go from the bottom, from the last row to the first row. And why is that? Because if we know that I and j, so for example, if you are calculating the value for this column here, so that column is basically it matches the third letter. So we are starting from the third letter, and we are ending at the last letter. So we have we have the substring A, B, and A. So that's the third letter, the last three letter substring that we are calculating the DP for. How do we know if ABA is a palindrome? So there are two cases. First of all, the first position and the last position have to match. So the elements, the letters that is in the original string that match the values indices I and J have to match. So that's the first. We already know that they match because we have I pointing to A and J pointing to A, so we have A equal to A, and we can just return true. Now, there are two clauses. There are two basically scenarios where we have a valid palindrome substring. The first one is that when we have only three characters. So if you have three characters and we have matching the first and the second and the last, then whatever we have in the middle doesn't matter because it will read the same from start to end and from the end to start. So in this case, we have the length of the string 3. So that basically matches the first scenario, 3 length substrings. So we know that we can place through here. So that's a valid scenario. But what if you're calculating if for example for the first row, last column? So that's the substring starting at the first letter and ending at the last letter. So basically that's the whole initial string. How would we know if it's a valid substring? So it's a valid substring because we have a matching here. We have A matching A. So I and J indices are pointing to the same letter. And now the second scenario is if the substring here is a palindrome. Because if it's a palindrome, we have two matching letters at the boundaries, basically at the beginning of the string and at the end of the substring. So if the middle is a palindrome, that basically means that the whole string, that whole substring that we are currently observing is a palindrome as well. So how do we know that BAB is a valid palindrome? So to know that, we will basically go into our table. We will go into the DP table. So we start from B, that's our second row, and we end at B. So this is the column that has to be, basically this is the cell that has to be true. So if we want to calculate dpij, and when I and j are pointing to the same letter, then also if you don't have a 3-length substring, then also the cell at I plus 1, basically that's the row below us, and j minus 1 has to be true. And as we can see here, j is now pointing to the last column, so we are interested in the column before it, so that's why we have j minus 1. And if that's true, then we know that the whole string is valid. So that's why we are kind of going from the bottom up here, because we need to calculate first B and B before we calculate the whole substring. That's why we are not starting from the beginning. So in this case, basically we will have quadratic. That generally when it comes to the dynamic programming problems, including the longest substrings and so on, because we always have these I and J pointers. So that will bring us to the quadratic time complexity, because proportional to the ends here are basically the length of the original string. And for the space complexity, we will have also a quadratic matrix, because we will calculate our DP for each of the cells. Now, the kind of complicated part of this problem is to reduce the space complexity to just n, to basically linear space complexity. But it's not that complicated if you see that we only need the previous row of the calculation for us to calculate the current row. And when I say the previous row, it's actually the row below us in the original matrix. So if we start from this row here, we will go up to this row and so on. So this row here will need the row below it. This row here will need the row below it, and so on. So we only need to contain one row, which contains n columns, because we initially had n times n matrix. And how do we know? How can we basically have this value here? Because we longer don't have a matrix. So basically, we know that dpj is true if, again, I and j are pointing to the same letter, and if dpj minus 1 is valid. So because we are going in the reverse order, we will not update the dpj minus 1 before we update the j. We will first update the j, the larger index, before we update j minus 1. So j minus 1 is pointing to the previous row. So once we are here at the first row now and calculating this here, we know that the j minus 1 is now pointing to this row here. So it's a previous row. And because we have j minus 1, it will point at this cell exactly. So basically, j minus 1 will represent either true or false for the substring that ends at the character just before our current j. So j is here pointing, basically in our case is the last column. But j minus 1 is ending here. And because we are decrementing I, each loop, I will be basically I will be pointing to here, the second element, for example, before we reach the first element where it's pointing here. So dpj minus 1 will basically tell us if this here is a palindromic substring, which we basically need. If we check the characters that are at I and j, and if they match, we just need to know if this is a palindrome. And if it is, then basically we'll just return true for the current dpj. So we'll just set it to true. If it isn't, then we can just set it to false because it's not a palindrome. Now we basically reduce the space complexity to n, to linear space complexity. So first we will get the n, which is basically the length of the string, and we will check if n is equal to 1. So we only have a string containing only one letter, so we'll just return it is because that's the longest substring that it's also palindromic, because every single substring containing only one letter or a digit is a palindrome in itself. Then we will create our dp, which will basically be an array of booleans representing if a certain substring is a palindromic or not. We will declare our max length to be set to 0, and the start and end will be pointing to out of boundary indices of the string s. Then we will basically iterate over our matrix containing basically n times n matrix, starting at the end. Same goes for the columns pointer, and then for each combination of I and j, we will calculate the dp, corresponding dp. And to do that, we'll basically just check if the current characters that I and j are pointing to are equal, and if they are, we will check if the string length is basically smaller than the 2, which basically means that between j and 1, j and I, we have 3 characters, and the last first and last are matching. So it's basically we have a palindrome, whatever we have inside of the middle. Otherwise, we have to check if the substring in the middle between the current I and j letters is also palindrome. And to do that, we already determined that we will just use the j minus 1 value of the dp. And if that's true, we'll just set the current value to be true, ending at the letter corresponding to the j index, and then we will just try to update the start and end, and also the maximum length. And to do that, we'll just see if we have a cold start, so we didn't have any max length. So in that case, start and end will still be pointing to -1, so out to boundary. Or if we have valid, we've already recorded some max length, we'll see if we can update it by using the j minus I plus 1, so the current number of characters between j and I inclusive. And in that case, we'll just update the start and end, and also the maximum length. Otherwise, we have a false for the current substring. It's not a palindrome, so we will just set it the corresponding value at j for the dp array. We'll just set it to false. Then we'll check after the 4 loops are done. We will see if the start is equal to -1. That means that we haven't updated start and end, so we can just return the first character of the string, because it represents a valid palindrome. We didn't find any palindrome substring of that has that's larger than one letter only. So basically, we didn't find any two letter size palindromic substrings in the original string. Otherwise, we have found, and basically we can just return the start and end using the start and end in the substring method on the original substring, although on the original string. Something to note here is that we are using n+1 because end is not inclusive in Java when calling the substring. So if you want to include end, we have to increment it by 1.